Hi, everyone. Good afternoon. So it's definitely a pleasure to see these workshop participants again. So last year I was talking about mobile phone type security, and but that kind of discussion was quite broad. So we look at all different kinds of vulnerabilities and security attacks, and some of the defenses against those attacks for around mobile applications. And today, so I want to dive a little deeper into a particular topic called sustainable defense, especially if we want to build a defense against evolving mobile malware. And particularly if you want to build a defense using machine learning approaches, because machine learning approaches are really popular these days. They have been used for building all kinds of solutions, including security solutions, and including security solutions against malware, and particularly for mobile malware. So why does mobile malware matter so much? Because we are all using mobile devices, and the major reason you want to use your mobile devices so often every day is because it has a lot of apps. Imagine if you have a mobile phone without so many apps there, you may not be really like using it so much. And but at the same time, the adversaries also take advantage of this. Take advantage of the dominance of mobile apps, mobile devices, and also taking advantage of the big population of the users using all kinds of mobile applications. And a particular security threat is, of course, malware. There are a lot of different kinds of malware. So the most recent statistics says there are probably more than 200 kinds of malware, so like different families of malware. And as a result, people built, mobile malware, detection approaches, classification approaches. So mainly around those things, but also some of the other forensics approaches and the tracking approaches using machine learning, because there are so many users using mobile apps. As a result, you got a lot of data, right? So you can train many powerful and vulnerable machine learning models to hopefully generalize from one situation to another, because it's kind of reasonable if you have a huge amount of data as a training set, the trained model should have a good chance to capture unseen kind of applications, especially when those unseen applications may have malware that has occurred before, or maybe it's very similar to some of the malwares that have been observed before. And today I'm going to talk about mainly two things. The first thing is one of the projects built in my research group, and we use a dynamic approach to build a unified approach, a learning-based approach to defend against mobile malware and particularly Android application malware. And then I'm also going to cover three more recently published papers at top security conferences, also addressing this topic, so that everybody here can get a kind of picture of what this problem is about, and what are the current solutions, and what are the most recent challenges. Even with respect to the most recent advances, we are not solving all the problems yet. There are still some challenges ahead, but there are also some promising solutions potentially. So I'm going to also look forward to those kinds of things at the end of this talk. So as I said, in the first part, I'm going to talk about the approach that was built in my group around like 2 years ago, 2 to 3 years ago, actually. And in this case, in this work, we particularly look at the Android malware, because I don't know how many of you actually are using non-Android device. Maybe if you have more money, you can buy Apple devices. But personally, I use Android most of the time. I believe most of our students are also using Android devices. So Android actually takes the dominance since very many years ago. And this dominance has been continuous over the years. So here, yeah. So this is a bit kind of an old data, but still the trend is actually keeps going. This data was sampled in 2019. So when this paper was initially written, so this paper was written in 2019 and then was published in 2000. So that's why I said this work was done like 2 or 3 years ago. And if you look at all the different the distribution of mobile devices in terms of the underlying like operating systems, you can see we have Android devices, we have iOS devices, and other kind of mobile OS, and also Windows Mobile. Probably this number is probably a little bit bigger today, but overall Android has been always the dominant platform, and that's one from one perspective. If we look at how people search on the internet about all kinds of things, from what kind of platform they're using internet search, like 74% of the searches are actually launched from Android devices, according to this website. This is a pretty, I would say, pretty, reasonably like popular website for web statistics. Like basically, calculating how many visits your websites have gotten like every day, and what are the sources of those connections, things like that. But basically, in summary, mobile applications are mostly running on Android devices. So that's why we look at Android. And in terms of as an academic researcher, I look at Scholar, of course, intuitively because I use this a lot. So actually, if you search Android malware detection, or maybe just Android malware or mobile malware on Google Scholar, and if you only look at the results since 2022, you got more than 3,000 results. That means there are at least probably 1,000 papers on this topic. But the reality is, malware continues to increase. So with so many approaches are being developed, I mean the landscape of mobile malware is actually expanding. It's not actually shrinking, which means there must be a problem there. And we look at this and we identify one of the problems is because this diagram actually shows the malware actually keeps growing rather than decreasing. When you have so many different malware defense solutions, which means they're not really deployed in reality, or maybe they have been deployed because they're not very effective, because they're not able to stop malware from growing. And one of the root cause we identified is because the underlying population is evolving. They are keeping changing. And this problem causes actually 2 consequences. One consequence is the malware can evade the detection because they have evolved. So let's say you have like several thousands of applications that were developed in 2019, and you use those applications to do your either supervised or unsupervised learning based classifiers to classify a given application as malicious or benign. And it works pretty well for that year. But then next year, the applications are changing a lot. So not only the applications are changing a lot, also the underlying Android platform also changes a lot. Right? If you look at how many versions Google has released since the debut of Android, it's actually more than 10 versions now. But how old is Android? It's also about like 10 years old. More than 10 years old. That actually was launched in 2008, maybe 15 years. But now you have about 12 different versions. So maybe around every 1.5 years, there's a new platform that has also emerged. So with both the underlying platform and applications evolving, you can imagine that the approaches that you build on the training data set in the older days, they may not be able to capture the newer versions of the applications that may be malicious, right? And there's another problem that's more like a software engineering problem, but that's not what I'm going to cover today. But I just want to mention that this root cause actually causes a lot of problems, not only for malware evasion, but also for a lot of compatibility issues. I don't know whether you guys have experienced that. I experienced that a lot. So I have a relatively old mobile device, Samsung Galaxy S9. It's pretty old today. And I'm not able to run many of the really wonderful applications that were developed some years ago, but they have not been updated to the most recent mobile device and mobile platforms. And as a result, if you're trying to run those applications, you get a lot of crashes. They're not working. The reason is because the platform changed, but the application was developed for the older platforms. For example, you use old APIs. One way the applications interact with the platform is through APIs, right? But that's actually the major, by the way, the most recent three works I'm going to cover at the end of this presentation, they're all use APIs, based features to build learning-based model detection approaches. So API keeps changing. And if you use the old APIs to build the application, and of course, those APIs are not going to be recognized or executed correctly on the newer platforms. As a result, the application will crash. Yeah, but again, so let's just look at the first consequence. So the security consequence is the malware may not be able to be caught on time using a learning-based model. And in our work, in our approach, we particularly look at this dynamic approach. And the reason is because they are actually using the runtime behaviors we observed during particular operations of the app. So basically what you get is so what you see is what actually happens. And you use those kind of behaviors to engineer some features. And then you use the features to detect, to build the learning-based detection. Then that kind of approach, of course, is intuitively very precise, right? Because I mean, what you have detected, it must be something that really happened. So as a result, very little false alarms. So everything that is reported must be most likely very pretty much true. But of course, it also has some drawbacks, right? So what the drawbacks might be? And that is, you may miss some of the true malware, right? So your recall may be low, but your precision will be pretty high. And the good thing is also, because we are actually running the applications, so rather than estimating the applications as in static approaches, dynamic approach is also good for adaptive detection, right? Because I'm actually running this application. So if the application can run, that means there may not be any compatibility issues at all as initially. So at least you can make sure that the application actually will work on this platform. And we also do what we call the unified detection. So in malware detection, there are two sub-problems. So one is called detection, so which is a binary, which is a binary classification problem. So you detect the malware as either, you detect the application either as malicious or benign. But there's another problem, which is more fine-grained kind of analysis, which is we want to go beyond the binary classification to tell what kind of malware this is, if this is malware, or what kind of, because the kind of malware actually points to you the kind of behavior that malicious may have. And that actually helps a lot with security analysts to further inspect what is wrong and how to come up with effective response. Okay, so these things may not be the most interesting things, but in this work, particularly we look at this relatively new problem back then, not now. Now it's not a new problem anymore, but when this paper was published, we are actually among the first who identified this sustainable problem, sustainability problem. Why sustainability is essential? So this is the definition. We have a manifesto about sustainable defense. And this kind of defense is because we believe an effective learning-based malware defense solution should not only provide good numbers in terms of accuracy for a particular training data set, or even for a particular testing data set. We actually care more about how sustainable this model can be. The reason, again, as I said, the data set keeps changing so fast. It's actually faster than desktop applications. if you imagine like Windows, I mean, it's updated not so often, right? So from Windows 10 to Windows 11, it takes probably 2 or 3 years. But for Android, there are so many applications. I mean, for 2 reasons. The platform is changing much faster than desktop environment. Second thing, the volume of applications is much greater in the mobile arena than desktop domain, right? For those 2 reasons, the manifesto is actually more important for mobile malware defense than maybe desktop malware. So that's why we believe they should keep the desirable capability of performance over time without keep updating the model. I mean, if you can update the model, maybe the problem can be mitigated, but it may not be entirely avoided. So why is that? So first thing, let's say you can update the model frequently. And that assumes you always have the new samples. You always have the samples of the new malware. So let's say there's a new kind of malware that emerged, maybe 0-day malware. And you can get a very good number of samples of that new malware. Actually, this assumption is mostly not valid, right? Because you won't be able to get those samples. So even if you can get the samples, you still may not be able to capture all the full scope of the behaviors of the new malware, right? But the reality is that you won't be able to get those new malware in the first place. So that's why we define sustainability like so. So we are assuming something that is realistic. We are assuming that something that is real in practice. You cannot frequently update the model. As I explained before, why cannot? Because of the overhead, but more importantly, because of the sample availability. You cannot get the sample. So that's why we want to develop sustainable defense. So our approach is this. When the Android applications keep evolving, maybe the malicious behaviors in some of the applications, they are changing with respect to some features, but not to all of the features. Or in other words, there may be some features that are not changing over time, right? Not everything is changing. I mean, if you look at Windows, from Windows 10 to Windows 11, has everything changed between the 2 versions of Windows? Not really. Some of the things change, many of the things are not changed. But we want to capture those things that have not changed, which means we want to find the features that are more robust against evolution. So that's the approach. So that's why we want to understand how the applications evolve. And because we are focusing on dynamic approach, so that's why we want to see how the applications approach in terms of random behaviors. Okay, we want to conduct this study. Why do we want to conduct this study? Well, because we want to identify the features that are good features. They're more robust against their evolution, as I just mentioned. Okay, so, and particularly we want to look at execution structure, basically particularly for the behaviors. How can we characterize the behaviors? We characterize the behaviors by looking at the code level execution structure of the applications. And how the benign apps are different from malicious applications in terms of those structures over time. And we have done that. Yeah, we have collected 2 data sets. We have collected data sets. Again, this paper is relatively older. Okay, this is the oldest paper among the 4 papers I want to cover today. This is our paper. So in this paper, we actually collected data up to only 2017. Because the paper was the study was started in 2008. That's the second year since I joined WSU. I was working on this project by myself. Yeah, that's why actually, if you look at this paper only has 1 author because I don't have students back then. So we collect the data sets for 8 years. Remember, Android was launched. The Android project was launched in 2008. So you really don't have so much data to collect before 2010. So that's why we started data collection from 2010, and we collect the data up to 7 years later. For both benign and malware, for each year, we aim to collect at least 1,000 applications. So by the way, I guess briefly mention, so I guess probably my presentation is a little bit kind of less hands-on, it's more research focused. So because in recent years, I mainly focused on security related kind of research. So I hope this kind of complements to other presentations which are probably more hands-on. But remember, many of the projects we are talking about here can be definitely deployed, and they can be definitely utilized in practice, especially the ideas. Hopefully, that can also help all of you guys if you think about developing some cool tools later. And so here we collect at least 1,000 apps for each year for each of these two categories. And in total, we have these roughly balanced data sets, and we conduct the profiling. And remember, in reality, you cannot assume this. When you build a learning-based approach, you cannot assume that data sets are balanced, especially when you think about a security-related problem. Mostly positive examples are much fewer. Do you agree? Right? So most of the time, for example, if you want to take vulnerabilities, most of the code in the real world, at least they are not known as vulnerable. Maybe they're vulnerable, but you have not detected it. So you have to assume they are not vulnerable. And the majority of the code is normal. They're not vulnerable. So that means there's a very highly unbalanced kind of data set in real world scenario. So when you build a learning-based model, you have to assume that they are not balanced. But why are we using a balanced data set here? Well, because our work here is to conduct a study. We want to conduct an empirical study to compare the behavioral profile of benign applications versus the behavioral profiles of malware. So in order to avoid the bias in the comparison, we managed to make the data set as balanced as possible. But why we have so many different numbers? Why not just use this one single unified number? Well, there are some difficulties because we are conducting dynamic characterization, which means we have to run the applications. You guys probably cannot imagine how fun that was. Maybe around 2019. I think during the summer, I always sit on my computer. I have another computer on the back. And I'm always using the monkey to trigger all the applications. And you can always hear some music playing, some of the chess moving. So because the applications are being played by the monkey tool. So, because I cannot just sit there and play so many apps, right? So yeah, the dynamic profiling actually took more than 1.5 years to finish because we have so many apps. And we aim to exercise every application with at least 15 minutes using monkey. Many times the monkey was not very lucky. They're not able to get into the application because they get stuck with the login interface. So most of the time was wasted. But also there are still a pretty good number of applications that can be exercised sufficiently. Okay, that's why. So, and many applications, they just crash immediately because of the compatibility issues I mentioned. Okay? And because of that, you cannot really get, if you really try to get the same number of applications to use in each year, you have to try many more. So, and because of that, we kind of gave up, we don't intend to do that. And that's why we have some very uneven numbers across all the year, but roughly every year you have at least 1,000. And we characterize this. Now let me go to the most interesting part. The most interesting part is something about the results. So we characterize, as I said, the execution structure of the code in the Android applications. For example, of course, we look at many different kinds of aspects of the execution structure, but this is just one way. We look at how 3 different layers of the code interact. Why does this matter? Because as I said, Android application is a very heavily framework-based application. Maybe some of you have written some mobile applications. If you have that experience, you probably agree with me. that as a developer, as a mobile application developer, usually you don't have to write a lot of code because many of the things have already been there, right? They're already provided by the framework. What you are going to do is most likely just filling some blanks, overloading some of the callbacks, things like that, to handle some of the events. And as a result, most of the time, the framework does the most work, like SDK. That's the SDK layer. But in order to build all different kinds of applications, you also want to use many different kinds of third-party libraries. And finally, the user code is what the developer actually wrote. So these three layers of code interaction reflect not only the behavior in the application themselves, but also how the platform, interact with the third-party libraries, but also the applications, which actually cover a bigger scope of behavior in the Android ecosystem, rather than just application itself. So that's why this execution structure is actually very interesting to look at. We also have to look at other features that I said. I'm just using one example to demonstrate how malware is different from benign. So this is the malicious apps. You can see very clearly the difference. So in terms of the distribution of the cross-layer function calls, so this arrow represents the function calls. So what we do is, among all the function calls in the application code, we look at the distribution of the three layers. We look at the distribution of those calls, those function calls, across the three layers. So for example, you have a function that is in the user code, and that function calls another user code function, then that gives one data point for user code to user code. And similarly for the other 8 different kinds of interactions. And the overall distribution is all the function calls, their distribution over the line categories of cross-layer interactions. So you can see the difference. And so I'm not going to dive into this, but the main point of this slide is both of them have decreasing calls with user code and increasing calls with SDK, right? This is one observation. So this is the implication within SDK, from SDK to SDK. So you can see in the later years, in the later applications, fewer and fewer application behaviors are actually reflected in the user code, which means the SDK is getting bigger and bigger, and the user code is getting smaller and smaller in terms of the portion of functionalities in the application, right? Because most of the function calls you can see, like almost like 55% of the function calls, they happen within the SDK. I mean, not even from SDK for third-party library, not even like from SDK to user code, even not including those two layers, just within the SDK, which means the Android platform does the majority of the work. And but in the early days, that's not the case. I mean, the early case, you have a lot of user code interact with the SDK for most of the functionalities. You can see that part. But later and later, that becomes very small. So this trend is important because if you actually want to understand why the malware detector built on early training data sets cannot capture the later malware, I mean, you can sort of get some idea why that's the reason, why that's the case. Because many of the behavior changed. You still use the older kind of data sets, which reflect the older kinds of behaviors to build the model. The model will definitely, of course, will definitely not be able to capture the newer versions of the malware. So this just give you one, but still we actually, from all the different kind of aspects of the characterization, I mean, I just showed you one aspect. This is just one aspect, which is called the cross-layer calling. So cross-layer calling is one aspect of our characterization. And so in terms of this characterization, it's not very consistent. So over time, the difference between malware and benign is not very consistent. That matters because we want to build the, let's say we want to build a binary classification. What is about binary classification? Knowing the decision boundary, right? But if the decision boundary keeps shifting, then the model fails. So that's why the difference matters a lot. We want to see how the benign and malware, how they are different over time. In early years, they are different like this way, but in later years, they're different in a different way. So, and among all the different features, we identify some golden features. So what are the golden features? These features are really nice. So even though if you look at their absolute values, they actually keep changing, both in benign applications and in the malware. But the golden part is they can always be differentiated, consistent. For example, in terms of this feature, in terms of the call side, targeting a sink. So this is one of the particular features we look at. And in terms of this feature, I mean, they are changing, in each of the two groups, right? In benign and malware. But in benign, this one is always higher. That's good, because that actually helps, the model to learn the decision boundary. I mean, intuitively, you can think of this way. If you have this kind of differentiation, I can always tell, based on this feature, I can also tell if the feature is higher, then that is benign. If it's lower, it's more likely a malware, right? So, and similarly, for the other feature is the opposite. So malware is always higher in terms of the calls targeting a vulnerable sink. So sink and the source, so these are like some function calls that retrieve sensitive information or likely sensitive information out of the application's memory space. So that's what we define source and sink to be. So I just want to give you the high-level intuition, how to build a more sustainable kind of learning-based model. So we want to identify the features that are not so jumping around over time. We want to identify the golden features. And then using those golden features, we only use the golden features to learn the supervised learning model. So that's why we developed, so we first introduced this concept. I mean, this concept is used very commonly, but we were among the first who proposed this performance metric called sustainability, because in the past, people only care about precision. We call true positive rate, false positive rate, detection rate, those kind of metrics to evaluate a detection technique. But we believe we kind of democratize this performance metric called sustainability. And we use the approach I just briefly introduced to build a technique called the droid span. And we compare droid span with the 5 state-of-the-art learning-based malware detectors. So let me see, because of the time, I probably want to go a bit faster. Yeah. Oh, okay, thanks. Yeah. So we define sustainability as 2 sub-metrics. One is called reusability. So let's assume that you have the samples to retrain the model. So for every year, so let's say we know we have some kind of 0-day malware in 2023. Let's assume that we can get some new samples of those malware, and we can use those malware to retrain the model. So then how well the model can keep this performance. So that is called reusability. We reuse the model because we can retrain the model. That's called reusability. And the other one is without retraining. So we are not going to update the model. We just keep using the same model which was trained some years ago and see how that model works against the new incoming applications of newer age. So that is what we call the stability. And this one is just one number, the accuracy, and this is a tuple. So it includes 2 numbers. This metric includes 2 numbers, the accuracy and the span, so y minus x. So basically, we train the model on the applications of year x and test them against the applications of year y. And we are sure that y is greater than x. So, and of course, the longer the gap, the more difficult to get higher accuracy for this one, intuitively. However, we later found that actually they are not really highly correlated, which means it's not necessarily like the greater the gap is, the lower the accuracy. That's not always the case, which means the model deterioration is not necessarily monotonic. Okay, we will look at some of the numbers later. I guess the detailed approach may not be the most interesting things to this audience, so let me just keep that. So overall, basically what we do is that you first instrument the applications. Basically, you insert some props into the application so that when you run the application on the Android device, we run the Android device, and you generate those traces of method calls. And then we build what we call a SAT profile, I was actually very glad that I used this name because this name is really to the point because how sad this app is. The sadder this app is, the more likely it's malicious. So we use the sadness to characterize the maliciousness of the application. And we build a kind of analysis representation called the timestamp dynamic call graph. Based on this call graph, we compute the features. And then we use the features to train whatever kind of supervised machine learning models, not deep learning, just ordinary machine learning models. Like random forest, SVM, yeah.
So this basically just looking at what functionality the app is doing.
Yeah, all the different kinds of functions.
What you found out is like, if it does a lot of this type of call, it's called malware.
Yes. Yeah, intuitively that's true, yes. And by the way, if you look at all the different papers on this topic, that's basically what they do. So look at the codes. We actually look at all the codes. Most of the recent research only look at one particular code, which is the API. They only look at the code to APIs. We actually look at the code to all kinds of methods, not necessarily APIs, including the user level applications, user level function calls, not just APIs. Because APIs are the methods provided by the framework, right? That's called APIs. Those are called APIs. And we use this kind of data sets. We build again. We use a similar kind of data set we use in the characterization study, and we evaluate that against the 5 state-of-the-art malware detectors. They're not. Some of them are still considered state-of-the-art. Some of them are not. And so here, this is the table shows the comparison of the 5 baselines against our approach. So the winner, the number of the winner, the winning number is highlighted in boldface. So we can see we actually won in most of the cases. But in this case, we did not. But in most of the cases, we actually have the best accuracy. So this is actually about reusability. So we basically just use the samples in 1 year's data set to train the model, and then test the model against the apps in that same year. So that is this is the reusability, and then we look at the stability. In stability, what we do is this. Okay, so let me explain how to read this result. You don't have to understand all of this. If you understand one of these bars, you can understand all the rest. So on the x-axis, we can see these 7 groups. So what does this mean? So this means for this group, we train the model using the samples from 2010, including 2010's benign applications and 2010's malicious behaviors, malicious applications. And then we test the model against the benign apps in 2011 and the malicious apps in 2011. Basically, only 1 year gap, only 1 year. And then do the same. So how about train the model also on 2010 applications, but then test the model against 2012, and so on and so forth. And in this way, you can build in total of 28 experiments. So here you only see 7. Because you use the data in 2010 as a training data set. And you test the data in applications 1 year later, 2 years later, 3 years later, up to 7 years later. But you can also do this similar kind of thing using the application in 2011 as a training data set. And then you can test that model against the applications in 2012, 2013, up to 2007, 2017, right? So basically you can imagine if there's another row, because this is a presentation, I'm not showing all the results that can be found in the paper. So we can see that most of the case, yeah, so our approach definitely wins. And this is like a summary result. This is like a summary. So average, on average, this is our approach. This is the other 5 state-of-the-art, malware detectors. So this is how they compare with only 1 year span up to 7 year span. So you can see what I just mentioned earlier, the deterioration of learning-based malware detection models is not monotonic. So you can see it's not like the longer span is definitely more difficult. That's not always the case. Because malware evolution and benign application evolution does not follow monotonicity, right? So that's why you do not have that kind of, like monotonically decreasing or increasing kind of curves here. Okay, this is the overall stability. So we have some edge over the baselines. And we also conduct some statistic analysis, some very simple statistic analysis to see whether the difference is really significant by looking at both the p-value and the effect size. And we also look at efficiency. I think efficiency is not so interesting here. Okay, so that is our approach. This is our approach. This approach is relatively old now, but it's still being cited by later approaches. And let me see, I still have like about 15 minutes. I'm going to talk about another approach, which actually represents more cutting edge kind of approaches, so that you can get some sense of how this research area has been evolving because we look at how applications are evolving, but how the research actually also evolves. So this is just our approach. And so there are 3 representative approaches. One is 2019, published at Euro SMP. So Euro Symposium, this is actually a new conference, very new conference, but it's actually very popular. It's gaining the popularity very quickly. It now becomes one of the really decent conference, not a very top, but very decent conference. And this work happens to actually appear in the same year as our paper, but they have adopted a very different approach. So I'm going to go through the main ideas of these 3 papers, but I'm going to dive a little deeper in one of the papers, which is the second one, because I believe that one is actually, to me, is more interesting and more kind of insightful. So the first approach is, their idea is this. So now, because if you train one model, right? If you train one model using a particular data set, a training data set, and this model will deteriorate. But then how about this? So can we train what we call the online learning kind of models? Because online learning means, okay, I take the incoming application as a streaming data. I keep changing, I keep updating the model. So as long as there's more data for training, I would just keep training the model. I'm not going to stop. It's not like a one-off kind of thing. But in addition to that, I'm going to use 5 alternative models. I'm going to try 5 alternative models and put them in a pool. This is basically the idea of major voting kind of idea. So if one thing becomes very bad quickly, so how about we have 5 things? And then I can hope that maybe some of them are getting bad slower. If others getting bad quicker, then I still have something to use. So that's basically the high level intuition. So what they do is that they use, as I mentioned, these 3 approaches are all based on APIs, not just, they're not only based on methods, but also particularly for API methods. they use the API, like whether this API occurs. So basically they analyze all the possible API calls, all the possible API, because you can actually go to the website of Android SDK documentation. You can get all the APIs in the SDK. And then what they do is that they use the binary vector for API occurrence. Basically, if this API is calling this app, then that feature is 1, otherwise it's 0. They're very simple. It's more like a one-time coding embedding. And then for all the possible APIs in the SDK, they can get a feature vector for the entire application. So basically, their feature is very simple. And the key novelty of this paper is this idea, a model pooling. So they built 5 online learning models, and they use weighted voting to consider which model maybe plays either role versus others based on some other kind of observations. And then what they do is that if some of the models becomes aged, then they will use the less aged models to update the more aged model. So basically, those models in the pool are helping each other to get updated incrementally. And the result is that this kind of Android malware detection system can self-evolve. So I mean, the major idea of evolution comes from 2 ideas. One is they have the online learning paradigm. The second is they use the models among the pool to update each other. How they detect which one becomes aged quicker? I mean, you can use some testing data set to check. I mean, you can use like the data sets with some gaps, right? You can use a newer data set to check some of those 5 models and see which one has lower performance, which means that they are aged faster. So this idea is reasonably effective, I would say. But the next one, I believe, is more interesting. So this paper is published in 2020. By the way, CCS is one of the top conferences in security. And so their idea is that I'm not going to be so ambitious to try to stop this kind of a model aging problem. I only try to slow it down. So how can we slow it down? I will leverage the similarity of our. Actually, it's very similar to our, but they have approached it different ways. They approach this kind of observation in different ways. So what they do is that they look at the API semantics similarity. So because applications use APIs to really exercise the functionalities of the device. So if you have a mobile application running on a device, how the application leverages all the functional features provided by the hardware in the device through APIs. Right? That's the only way you can do it. For example, if you want a GPS location, you have to call the API. Otherwise, you won't be able to get the location. If you want to access the battery status, you also have to call the API. If you want to send a message out, you also have to call the API. Most of the things are, basically they boil down to API function calls. So what they do is they build. So I think that let me just jump to the real example. So I hope this example can help you understand the motivation of this approach. So these are the 3 versions of one kind of malware called Xloader. Xloader is one particular malware. You can search, don't try to install. If you install it, may cause some issues immediately. So because this malware is still active, I did search today, and they're still being monitored. So this malware, if you look at the 3 versions, in the first version, why this malware is considered malware? Because it collects personally identified information, PIIs. So in the first version, it only collects the device ID. But in the second version, it also collects the MAC address in addition. And in the third version, it further collects the serial numbers, the serial numbers of the SIM card of the phone. Right? You can see these 3 different versions of the malware has some, changes in their behavior. And that changes can be summarized as collecting more and more PIIs. So that is the information collected. And then what really makes this application malware is they are sending those kind of PIIs out of the phone. So, and they have different ways to send that information out. In the first version, that is done by using HTTP, using URL. In the second version, they use socket. In the third version, they are using SSL sockets, the security socket, the secure socket. So these are the different variants of the same malware. So this also reflects how the malware has evolved over the years. So through these three different versions. So how can we capture this kind of malware? So let's say if the model can detect this malware, how can we make the model not to be fooled by the newer version of the malware? Or in other words, if I have built a learning-based malware detector that can detect the version 1 effectively, can we also make the detector detect the second and the third version of the malware as effective? So that's the idea. And the motivation is to leverage the semantic similarity of the APIs. And this is the idea summarized here. What they do is they build what we call what they call, not I call, so they call the API graph. So in the API graph, you can see these are three sensitive APIs, right? So open connection, and that's this API, because that's the malicious behavior is reflected in this API call. So in this version, this is the malicious API. In the second version, building the sockets. So that is the second malicious API in the second version, and this one is in the third one, in the third version. So these APIs, they have some permissions. So this is one of the mechanisms I think I covered in 14.8. So in the Android operating system, in many other operating systems as well, permission is one of the basic kind of security mechanisms. So you use permission to protect who can access what. So because these kind of API capabilities can only be accessed using the corresponding APIs, then we want to protect who can use those APIs. So only the user who have the permission can use the APIs. So these are the permissions used by each of the APIs. And that is another aspect of the behavior of the API, right? And also there's another behavior, which is what kind of exception that might be thrown when the API is called. Because when you call any API, it's possible that there may be an exception to throw. So considering these two aspects, the API itself, and also the permission that is required for calling this API, along with the exception that API invocation might throw, we can connect their relationship using the edges, and we can use the nodes that represent the permissions and the APIs and the exceptions. And this is what they call the API graph. And based on this API graph, anything that is in one graph, you can consider them as one cluster. In other words, you can consider these three APIs as very similar or even equivalent. Okay, then what is the benefit of doing this? The benefit of doing this is because they are considered as one cluster, then later, when you build an API-based feature kind of machine learning models, instead of using individual API as features, you can use the API cluster as a feature so that the evolved version of the malware, they will be considered similar to the early version. That's how you can capture the malicious behaviors in the market. And what they do So this is the approach. They built this API graph, API relation graph, which is this. And they use the clusters embedding and adding this embedding to the existing malware detectors embedding space. Basically so replace the original API, individual API-based features with API cluster-based features. Because again, API cluster captures the similarity among all the APIs in that cluster. And that is how you can capture. You can actually explicitly tell the model which APIs are considered very similar or even equivalent, so that the model can be, improved to detect all the different variants of the same model. So these are considered different variants of the same model, different versions. And they have some interesting results here. In one way, they evaluate the usability, the merits of this approach in terms of if I want to add new labeled samples in order to update the model, then how much human effort I can save, how much labeling effort I can save. The blue curve, the blue shows will you use the API graph approach. And the red one shows when you don't use the API graph approach. And the y-axis is the number of labeled samples you need. So you can see you can save a lot of effort. And the x-axis here shows the different gaps. The different gaps between the testing data set and the training data set. Okay, and on different malware detection models. So this is one of the malware detection models. Very interestingly, we also use this model in our evaluation. Do you remember that? Right? This is one of the malware detectors we also use in our evaluation. And they have looked at several other malware detectors. So basically, by using their cluster-based approach to replace the original API-based approach, they can improve many different existing malware detectors to slow their aging, to slow their model aging. And then in terms of the actual performance, to showing how the models are aged, how quickly the model can age. So they actually consider 0 to 12 months kind of gap between the testing and the training training time. So using the API graph, it slows down, the model ages much slower. It slows like this. If you don't use API, the API cluster-based features, the model can deteriorate much faster. So, and they show that their approach can help all the 4 detectors pretty significantly. And for this one, it maybe not so much, it still helps, right? And for this one, it helps the most. I would say helps this one the most in terms of the absolute numbers. Okay, I think I need to wrap up. I believe I started in 2:35. Yeah. I have 1 more minute, not including the Q&A time. So the third approach is just published most recently at the Auckland S&P. This is another top security conference. So in this approach, they exploit a conformal prediction kind of theory approach. And their goal is to deal with the concept drift. So this approach, I would say, is more comprehensive because they are not only dealing with API-based features, only look at the difference between malware and the malicious apps in terms of the APIs. They look at the whole data set characteristics, regardless of what kind of features you use. They use conformal prediction approach. Basically, you have multiple things, and you check whether one model conforms to that. So yeah, I don't want to get into this, but I just want to tell you, there are several different kind of approaches. And these approaches, the main goal is to identify what are the samples that are most likely to be misclassified. If I know they are going to be most likely to be misclassified, let me just reject it I'm not going to tell you the result because I know this result is not trustworthy. I know that I'm not sure about this result. So let me just reject it because I'm not sure. By the way, conformal prediction is one of the ideas using for uncertainty estimation. So you can, because machine learning models have uncertainty. For some samples, you have more confidence. For some other samples, you are much less confident. So if you're not confident about some of the samples, especially the samples that already represent the concept drift. So by the way, what is concept drift? Concept drift basically means your testing samples are no longer like the training data sets. In terms of distribution, it does not follow the distribution of the training data set anymore. So in this paper, basically they use this kind of technique to identify which samples I can reject earlier. So this is a very different approach, right? I'm not trying to slow down the model deterioration. I'm trying to reject samples that I may not be able to get confidently, so that I can tell confidently the results that I get. So that's how they actually achieve overall better ability for this kind of sustainable device. Okay, so what we learned is, deterioration may not be monotonic, and the concept drift is the root cause. I mean, even when the API evolves, that's also one of the reasons for that can also be considered one particular case of concept drift. And doing evolution study can help you design sustainable solutions, and you're not going to be able to eliminate the retraining. So maybe you can make the model deteriorate slower. Maybe you can make the model last longer, but you're not going to be able to make the model last forever without retraining forever. That's not going to happen. But still, we have some challenges, right? Especially for 0-day kind of malware, it's still going to be very challenging. And what we can do is, maybe you can build more malware samples, because one of the challenges is that for the new emerging 0-day kind of malware, we don't have samples to update the model. Then can we actually predictably generate the samples? For example, we can simulate how the malware evolves into the future, so that you can potentially create samples of those kind of possibly happening future malware behaviors. We use those samples and add them into the training data set to update them. So that's one possible idea. Okay, so that's all I have. So maybe I can answer some questions.
Yeah, I was wondering about the numbers you showed at the beginning for usage of Android versus iOS. Is that just in North America or is that global?
Oh, these are from Google Play. So you can see, maybe you can learn them more about.
Yeah, maybe there's some other mobile market, big mobile markets,
yes,
like China maybe is different.
Yes, very good point, very good point. Yes. So it really, the data source definitely matters. Yeah. But so Google Play is probably still the most popular app store, I think it's. Yeah. So this is one of the recent research topics. Well, actually, just before I came to this room, I looked through the Google Scholar. There are about like 5-10 papers on this topic, including one paper from a famous professor called David Wagner, which is one of the really kind of, I would say, one of the fathers in security. So he actually also wrote a paper about continuous learning for Android malware detection, which actually also deal with the same problem. So that means this problem is still worth investigating. If some of you are interested in this, you can talk to me. So I'm actually still working on this. Okay, do we have more questions? Maybe not now, so you can, if you think something later, you can send that email to me. Yeah. Okay, thanks everyone.
Thank you.